right? It's called chapter 10 old syllabus, but the new syllabus is chapter 6. And basically the syllabus hasn't changed much. Something added, something removed, that's all. Right? Minor changes. So that is the essential thing is the formula, stress, tensile stress, uh, strain, tensile strain, Young's modulus, spring constant, right? Energy stored in spring. So this summarize for you what you have to learn, you have to know. Okay, any comments so far?
Don't have.
Don't have, okay, let us try the question then. What's the answer for this one?
C.
Okay, good. C. Number 2. Write down the formula. The formula. Right? Make sure you try the homework at home first. If not, you are going to take a lot of time doing in class. Right? Take all the constant to one side. Yeah, told the same load, same material. So same load, force, same material. So AX and L take to one side. And then this is the original. This is the new length and the new extension. Okay, so you want to find x2, take this time down, take cross multiply, you got that. And okay, original is A1 is A, original length is L, original length is L, right? New length is double, twice, yeah, twice the original length, and 4 times the cross-section area. For A and A cancel, L and L cancel, 4 cancel by 8, you still got 2, so it's 4 millimeter. Can play with the formula only. Okay, how about this one?
Work done.
Say a bit louder.
C.
Right? You have to redraw the graph. Right? Force or tension against extension. So that's a new graph. Answer is B. That is the area. Okay.
Yep.
How about number 4?
Uh, Stress over strain, so I think it's D.
Okay, donkey. Okay, number 5. What is the answer? As a spring constant. What the extension time graph?
20. Okay.
What's the
Wait, wait,
answer?
wait. No, no, no.
Right, we draw the graph. Load against extension. Original length is 10 cm. So to find the extension, we need to minus the original length. K is load over extension.
A.
So load is 0.2. Extension, if we take 0.2, then this will be right, 12.5. Change it to meter. 0.01125 minus 10. 10 is 0.1. A. Okay.
Hmm.
Number 6. Oh, no, this is loading. You start from origin. You add weight, that's called loading. Then unloading, you remove the weight. The answer is donkey. No? Q is the net work done. Okay, no?
Yeah.
Number 8. As usual, we draw the graph. No? 20 cm is the origin, 20 millimeter is the original length. So we want this area. No? Need to subtract 20, need to subtract the original length 20 millimeter from L. Strain energy is shaded area, no? Area of triangle. Can,
Yeah.
how about this one? Yep, yep, yep.
Hmm.
Right? Remember, C, memory work only. Right? The extension changes from x1 to x2, so area under the graph on this axis. Right? Not on this axis. How about this one? Yep, yep, yep.
B. Wait. It's either A or B. But I think it's B.
Yeah, B. Right? These two must be parallel. This loading, this unloading must be parallel, not vertically downwards. This one, strength strain graph.
Young D. Wait. No. Wait.
Gradient is stress divided by strain. No?
The gradient is Young modulus. The area is work done. B.
Ah,
B, boy.
no. A.
What?
Work done per unit volume. What does the gradient represent? Gradient represent Young modulus. So, okay.
Yeah. So
Should
then what's
be
the work done again? I forgot.
work done is what you call that? Force against extension ground. No?
Oh, okay.
Okay, let's try this one. Draw the forces acting. Identical spring. So three springs share the load W. So force on each spring
B.
is W divided by 3. Right? They share the load W. So three forces divided by 3. No? And that's equals to Kx. Two spring. Now you remove the center one. You add 2W here. For two spring, right? The force on each spring will be W because they share up to W. Since the force, okay, W. So this is W. The force on each spring is W, and it is Kx is W over 3, so it's times 3. K is constant. Okay, donkey. Okay or not?
Yeah, I thought the extension is supposed to be lesser because it's the weight distribution is to three springs.
The weight on each spring is W. So to get W, you must multiply by 3. 3 here and 3 here. So it's 3x.
Oh,
Okay. How about this one? Right? Draw a straight line to 5 meter, and then the area under the graph, energy stored must be less than the area of triangle. Area of triangle is half 40 Newton times 5 100 joule. Can
yeah.
try this one. Maybe with the formula, that's all. Which is formula? Same material, same Young modulus, same extension, same x. So take all the constant to one side. You got this constant. FL over A is a constant. So this is for wire P, this is for wire Q. So FP, L, P is L, Q is 2L, P is A, Q is A over 2. So take A and A cancel, L and L cancel, times 2 here, times 2 here, it becomes 4. This one 2 eliminated. Take FQ down, you get 4. Answer is donkey. Okay or not?
Yeah.
A ductile material is stretched by a tensile force to a point beyond its elastic limit. The tensile force is then reduced to 0. The graph of force against extension is shown below. Which area represents the net work done on the sample? Yep. What's the answer?
Y.
Say a bit louder.
B.
Net work done is area under the graph. This area. B. Z is energy recover. Okay. Energy recover, that means your work done is returned to you. Part of the work done on the wire is returned to you. Okay, Yep. What's the problem?
Yeah.
32. What's the answer?
Compression for X.
What's the answer?
Uh, Tension for Y. Eh?
Yep. What's the answer?
Wait,
It will go like that because this load is pulling it down. This one cannot move. So you bend. So this is tension,
C.
tension. This part is compression,
C.
right? So B, boy. Okay.
Ah.
What's the answer? Yep.
C.
Boy. Right? Yes. Y is either less than elastic limit or elastic limit. So you when you unload it, you will follow the same line. Right? Haven't exceed the elastic limit, so it's not in the plastic region.
Joe, what's elastic and plastic again? I forgot.
If Y is the elastic limit, then when you remove the load, it should return to the origin.
Yeah.
Whereas if you exceed the elastic limit, it will not return to the origin. Okay,
Oh.
like this case, exceed the elastic limit, it comes down parallel. This one and this one more or less parallel. Okay,
Oh, plastic.
plastic. That means it doesn't obey, it doesn't, the wire has been changed already. It is a bit longer already. Something happened in the inside of the wire. We don't need to know too far lah. You just know that it doesn't return to its original length. Okay,
Yeah. So elastic returns to its original length, but plastic doesn't.
elastic, it will return to its original length. Plastic, when you remove the load, it doesn't return to its original length.
Okay.
Try this one. What is the best estimate of the strain energy stored in rubber band when it is extended 30 cm? Just break it out into triangle, triangle, and then rectangle. And then the strain energy is area under the graph. Right? Area of the triangle. Right? Area of this triangle. Area of this triangle plus area of this rectangle. Okay, now
Yep.
you have to roughly know we overestimate now, so we know roughly the answer lah. Don't overestimate too much lah.
Okay.
Okay, let's try this one. Don't worry about the first part. First part is outside the syllabus. So state the type of material which would produce the line shown in each graph. Right? They call it line lah, rather than call it curve lah. They call it line. So number one is graph A is what?
Elastic.
Right? It's either brittle, ductile, or polymeric.
Huh? Oh,
What material? Type of material. Right? Memory work.
brittle. Ah, copper. Oh, yeah, brittle.
A is brittle, B is ductile, C is polymeric.
What's
Okay,
polymer?
plastic lah. Plastic or rubber.
Ductile means like rubber band.
Ductile is steel, copper wire.
Ah,
Mm.
okay.
The idea is this is a straight line obey Hooke's law. After that, you got elastic limit. After that, you extend a little bit more. Brittle, it will go to the elastic limit, then it will break. That's the difference. Okay, use graph B to estimate the work done in stretching the specimen from 0 to 4 millimeter. Right? The area of triangle and area of trapezium. No? Shaded area. Can?
Yeah.
Yep. Can or not?
Yep.
State with reason whether the spring is undergoing elastic change.
No. Wait. Yes.
Reason?
Because there's extension. A
Reason?
significant amount of extension.
No hysteresis or no permanent deformation.
Oh,
So
yeah.
elastic change. Right? It returns your original length. Lah. That's the whole idea. Lah.
Or returns the original length. Okay.
Return the original length. Show that the work done is equal to that. Right? That's the area. That's the area. Work done is area under the graph. Line OQ or average also. Either you do that, right? And then replace the F1 and F2 with that formula there. Or you alternative is you take the triangle shaded area. How to get the shaded area? Area of this big triangle, right? That one. Area of this small triangle, that one. And then replace your F2 and F1. Okay, can.
Yeah.
That's to do with A2 lah. That's why I have to try it out for you lah. Okay, a trolley of mass 850 grams is held between two fixed points by means of identical spring as shown in figure 5.2. When the trolley is in equilibrium, the springs are each extended by 4.5. Each spring has a spring constant, given that the trolley is moved a distance of 1.5 cm along the direction of the spring. This causes the extension of one spring to be increased and the extension of the other spring to decrease. The trolley is then released. The trolley accelerates and reaches its maximum speed at equilibrium. This is called equilibrium when it's not moving. Assuming the spring obey Hooke's law, use the extension in B to determine the maximum speed of the trolley. Right? If you take original length of that, without the trolley, then this one is stretched 4.5 cm. This one is stretched 4.5 cm. Right? So you use the graph to help you. Right? You move to the left. Right? You move this one to the left. This one increased by 1.5 cm. This one decreased by 1.5 cm. Right? Left spring gain potential energy, while the right spring, this spring, loses potential energy. Gain in energy, gain in energy of trolley. Right? Just use the formula that we have derived just now. Right? This one is 6 x2. Right? Change it to meter. X1 is that. And then half k x2 is this one. 4.5 minus 1.5. You get that. Change it to meter. This is your x1. And calculate out and get 0.36 joule. And that becomes a kinetic energy. Half, right? Mass is given. Mass of trolley is given. Change it to kilogram. V square equals to 0.36. Then calculate your V. Can or not?
Yeah.
Right. Let's try something else.
Sure.
Yeah,
Do you have like something like this, but like a full partial paper?
this one I select from the parcel paper that I sent you.
No, I mean a compound one, like the whole year paper one.
I've given you already. I
Huh?
only select a few that I try with
Not chapter by chapter, the whole set. Whole set.
whole set. Whole set I have up to 2022, that's all. You
Ah.
can download it from the extreme paper lor, from the website.
Yeah, but because your PowerPoint slides have solutions.
My PowerPoint follow the past year paper that I send you lor. So it doesn't follow the year by year. Right? All I've
Oh,
compiled it is topic by topic until
okay.
2013.
Wait, so right now we're going through topic by topic, right?
I review with you, lor. That's why I'm asking you questions. Make
Ah,
sure that you know how to calculate some of the basic thing, lor. Topic by topic, lor. So the next topic will be waves, lor.
right.
Right? The past year paper I sent you already. So during the break, you can try waves, lor. Okay. A spring have a spring constant K hangs vertically from a fixed point. A load of weight L when hang from the spring causes extension E. The elastic limit of spring is not exceeded. What is mean by elastic deformation? Yep.
Uh, Extension does not remove to original shape. No, I mean yeah, change of shape.
Change of state when the deforming force is removed, we return to the original shape rather than original length. Okay, what's the relationship between K, L, and E? That's all. L is the weight. Okay.
Oh, yeah, yeah, yeah.
Usually we use F. F equals to KE. Okay.
Yep.
Now you should be able to fill up for me. Total extension.
What the total extension?
For one spring, with L, the extension is X or E. So with two spring, each of them the rate
2x,
to E.
2e.
Yeah, each of them extend by E, the same load. Each of them have the same load or same tension. Then to find the K, we take load over extension. Right? Load is L, extension is 2E. Right? We use the formula K is L over E, and L over E is K. So K over 2. Okay, try the next one. They share. So the tension in each string is L over 2. So X half E. Right? Half E. Then same, to find K is load over extension. Load is L, extension is half E, right? Times 2, bottom times 2 on top, we get 2, L over E is K. Okay now.
Yeah.
Okay, try this one. What's the extension? This one is E. Is E over 2 half E. Right? So we get that 3 over 2E. Then apply the same formula. K is load over extension. load is L, extension is 3 over 2E, right? Times 2 here, times 2 there, and then L over E is K. Yep, can.
Yeah. Yeah.
Okay, we probably have a little bit of time to do one more. After that, we go to waves. Right? From the graph, state whether the material of the rod is ductile, brittle, or polymeric. Right? That's the breaking point. Yeah, you stretch it until it break.
Ductile.
No, brittle.
Hey, no, yeah, brittle. I confused the word.
Determine Young's modulus. How to determine Young's modulus?
Stress over strain.
Just take a point. No need for gradient, take a point. Stress over strain, read the value, and choose any point. Right? Stress value, strain value, remember the power. Okay,
Yeah.
a second rod of the same material has a spherical bubble in it, illustrated in figure 4.2. The rod has a cross-sectional area 3.2 times 10 to the power minus 6 meters square and is stretched by forces of magnitude 1.9 and 10 to the power 3 Newton. By reference to figure 4.1, calculate the maximum area of cross-section of the bubble such that the rod does not break. Use the formula. Right? Maximum stress from the graph. Right? Maximum stress from the graph is 9.5. Okay, 9.5 here. Right? From the graph. Then stress is force over area. Right? Maximum stress, minimum area. Okay. That's the force given. That's the stress. There is 2 10 to the power minus 6 meter. Maximum cross-sectional area of bubble is 3.2. Okay, yes, 3.2 minus 2.0. Okay, now.
Yep.
Anything else you want to ask? We got less than 1 minute, so we will cut off anytime now. No point in starting anything. So
I don't
during,
have anything to ask.
okay, that's the last part.